What does a fractional derivative mean? For example, what could a half-order derivative, or even a complex number, the ith order derivative, mean? Let's figure out how we can make sense of this. First, let's look at some general patterns of nth order derivatives. For example, let's take a look at the power function. I'm going to use a shorthand operator notation here. We're just going to say d of n of x to the k, so the nth derivative of x to the k with respect to x. So we can do this kind of iteratively, sort of uses induction in the background, but let's take inside the first derivative. So we're going to get the k coming out. We get k times the n minus 1th derivative of x to the k minus 1. Then we get k times k minus 1 times the n minus 2nd derivative of x to the k minus 2. And you can see that the general pattern is going to be k times k minus 1 all the way down to k minus n plus 1 times x to the k minus n. Now, if we want to generalize this for fractional values, we can use the gamma function instead. See my gamma function video if you haven't. It's pretty important in this video. So gamma of k plus 1 all over gamma of k minus n plus 1 of x to the k minus n. How about reciprocal powers? If we look at the nth derivative of 1 over x to the k, again, doing this inside out, we're going to get minus k times the n minus 1th derivative of 1 over x to the k plus 1. Then minus times a minus, we get a positive k times k plus 1 times the n minus 2nd derivative of 1 over x to the k plus 2. And once again, in general, we get the pattern that this is going to be, it's alternating, it's going to be minus 1 to the n times k plus 1, all the way up until k plus n minus 1, all over x to the k plus n. And once again, we can use the gamma function here. We're going to get minus 1 to the n times gamma of k plus n all over gamma of k times x to the k plus n. Another example we can look at is the exponential function. If we look at the nth derivative of e to the kx, this one is probably the simplest of them all. You know, you keep getting these prefactors of k out in front, so we're going to get k times the n minus 1th derivative of e to the kx. Then you're going to get another k, and you can keep doing this, so the general pattern obviously is going to be k to the n times e to the kx. Now, we can also look at the complex exponential, and we can use this to get the nth derivatives of the trigonometric functions. Specifically, we have the nth derivative of e to the ix is going to be I to the n times e to the ix. And so then the real part, which gives us cosine, this is just going to be the real part. So e to the I, if we write this all in one power, we're going to get e to the ix plus I pi n over 2, taking out the I. So we're going to get cosine of x plus pi n over 2. And similarly for the imaginary part, for sine, this is going to be sine of x plus pi n over 2. So let's look at a specific example utilizing the fractional derivative for the power function. Let's take a look at the half derivative of x. So using the formula, we're going to get gamma of 2, that's 1 factorial, over gamma of 3 over 2 times root x. Gamma of 3 over 2 is square root of pi over 2, so we're just going to get 2 times the square root of x over pi. Now, for this to be a half derivative, you'd want to take the half derivative of the half derivative to be the single order derivative. So let's take a look at that. If we take the half derivative of this, of 2 root x over pi, pull out the 2 over root pi, then this is going to be 2 over root pi times gamma of 3 over 2 over gamma of 1 times, now we have x to the 1/2 minus a half, that's just x to the 0 or 1, it's constant. And once again, you know gamma of 3/2 is going to be root pi over 2. And so these are just going to cancel and give us 1, which is indeed the first order derivative of x. You can even, this doesn't stop you from plugging in complex numbers if it works through. This sort of blurs the lines between derivatives and integrals, but who says that we can't do that either? Now basically, this can be thought of as a smooth or continuous interpolation between the integrals and derivatives of these types of functions. Like on screen here, you see it goes smoothly between the derivative and integral of the function x. And basically from this idea, we can suggest one formula to be, if f of x can be expanded as the power series, sum n is equal from 0 to infinity of a sub n times x to the n, then we can say the alpha order fractional derivative of f of x to be equal to, and we can differentiate each term because of linearity, so we just have the sum from n equals 0 to infinity of gamma of n plus 1 all over gamma of n minus alpha plus 1 times x to the n minus alpha. Now the thing is that this is still not really like a specific formula, and then again, if you get the sum over here, you have to figure out what that's going to be, and it sometimes can be very difficult, especially in terms of closed form. So we're going to look at some more well-defined definitions, starting from an integral representation. So we're first going to start from a formula for the nth integral, nth repeated integral, because this is actually easier to find, and then we're kind of gonna do some integer order differentiation and then undoing that with integration in a way to get a fractional order derivative. So we're going to start, I'm going to use the notation I to the n, the nth integral of f of x. You need a base point here. The base point is a, so it's just the integral from a to x of the integral from a to x1, integral from a to x2, all the way to the integral from a to xn minus 3, a to xn minus 2, integral a to xn minus 1 of f of t dt dxn minus 1 dxn minus 2 all the way to dx3 dx2 dx1. Okay, and so what we're first going to do is change the order of integration. We want to take the t out in front. By Fubini's theorem, we can do this. So now everything after the outer integral is going to just be bounded below by t. We're going to get the integral from a to x. Again, you can pull out the f of t over here, of the integral from t to x, integral from t to x1, all the way to the integral of t x to the n minus 4, t x to the n minus 3, and t x to the n minus 2, dxn minus 1, dxn minus 2, dxn minus 3, to dx2, dx1 dt, like this. And now we're going to do a change of variables for the remaining n minus 1 inner integrals. We're going to let u of I to be equal to x of I minus t. Okay, for I is between 1 and n minus 1. And we know that the Jacobian determinant is going to be equal to 1 because this is just a simple shift. And so what this is going to do is going to make all these lower bounds here to be 0. and then you notice we're going to get the repeated integral of a polynomial function, which is pretty simple to figure out. So basically, we're going to get the integral from a to x of f of t times the integral from 0 to x minus t of integral from 0 to u1 all the way down 0 to un minus 4, 0 to un minus 3, and integral from 0 to un minus 2, dun minus 1, un minus 2, dun minus 3, all the way down du2, du1, dt. Alright, and so we can do this successively. So we're going to get the integral from a to x of f of t, integral 0 to x minus t, 0 to u1, 0 to un minus 4, 0 to un minus 3. We have un minus 2 over here, dun minus 2, dun minus 3, du2, du1, dt. And doing it again successively, we're going to get this 1/2 prefactor pulled out. F of t, integral 0, x minus t, zero to un minus 4. Now we're going to get un minus 3 squared, dun minus 3, all the way down, du2, du1, dt. Alright, and so basically, this is just going to get, here you're going to get reciprocal factorials, and these powers keep increasing. So basically, towards the end of it, this is until we reach the outer integral over here. And so this is n minus 1 integrals, is going to get all the way to the power of n minus 1, and then you have n minus 1 factorial out in front. So our formula is integral from a to the x of x minus t, this is from this part right over here, to the n minus 1 times f of t dt. Okay, so this is our definition of the fractional integral, and a straightforward way to generalize it is for the alphath integral, the fractional integral, we can just use the gamma function now. So gamma of a here, a to x, sorry, alpha, x minus t to the alpha minus 1 times f of t dt. Okay, now you see how we can't just put a negative alpha in here. Maybe with complex numbers some stuff is still going to work out, but specifically we cannot recover integer order derivatives because gamma of a negative integer is going to be undefined. So we have to figure out a smarter way of doing the fractional derivative from this. One way of doing this is to take integer order derivatives, basically the integer order being the ceiling of our fraction that we're covering, and then undo it by doing integration of that ceiling minus the original. You could also exchange the order of this. In fact, we have two main popular ways that depends on these orders. So the Riemann-Liouville definition, you have the fractional derivative to be this. This is where we have the differentiation on the outside minus alpha here of f of x. So you see we have basically it's I of minus ceiling of alpha and then plus ceiling of alpha. So then it kind of cancels and give us minus alpha, the fractional derivative. And then the other way, the Caputo definition, is just switching the order of differentiation and integration. So instead we're going to have I ceil a minus a times the integer order derivative of the ceiling of a of f of x. So these are our definitions over here. One thing is that these both have what's called non-locality because, remember from the fractional integral, it depends on the base point A of integration. So derivatives are not local anymore, at least not local until it becomes an integer. So it depends on other parts of the function. Though usually, from what I was experimenting, you can get back local-like behaviors if you choose A to be a vanishing point for the function, like 1 for the natural log of x, because that becomes 0 there, or limits like negative infinity for e to the x, because the limit as as x approaches negative infinity, e to the x goes to 0. But again, you don't have this for every function. So anyways, let's look at some examples of these. We can look at, here we're going to look at the nth order integral. Of course, you can also do this fractional, but I'm just looking at nth order here from how we defined before of the natural log of x. So this is going to be the integral of 1 over n minus 1 factorial. I'm going to choose the base point to be 0 because integrals of the natural log of x vanish with 0. They have x prefactors normally. So we're going to go from 0 to x of x minus t to the n minus 1 of the natural log of t dt. Okay, now we're going to do a substitution, u equals t over x, basically to get this thing to become a 1, this x over here. So, and after we do that, then ln of t here, it's just going to become ln of ux, split that as ln of u plus ln of x, and then we're going to get x minus xu, basically factor out an x to the n minus 1. And so that's going to become, with another prefactor of x here, so we're going to get x to the n over n minus 1 factorial of, so we have natural log of x pulled out, 0 to 1, 1 minus u to the n minus 1 du, plus the integral from 0 to 1 of 1 minus u to the n minus 1 times the natural log of u du. So we have these two separate integrals. This one is very easy to show that it's just 1 over n. So we're going to have x to the n over n minus 1 factorial times natural log of x over n, plus this integral. Now over here, I'm going to use what's called King's rule, which is basically just replacing f of x with f of a plus b minus x for integral from a to b. That's just a simple substitution. It's called King's rule. And so now we can switch this so that we have from 0 to 1. Now, instead of 1 minus u, we have u to the n minus 1, and we have natural log of 1 minus u du over here. And now we can use the Maclaurin series for ln of 1 minus u. So we're going to have x to the n over n minus 1 factorial times the natural log of x over n. Now we pull out here, we're going to have the sum k equals from 1 to infinity of 1 over k times, now we just have the integral of a power function u to the n plus k minus 1 du, right? And so this is going to evaluate to x to the n over n minus 1 factorial times natural log of x over n minus this sum right over here, k is equal from 1 to infinity of 1 over k times n plus k. Okay, now doing partial fractions on the sum and pulling another n out from this, we're going to get x to the n over n factorial times the natural log of x minus the sum, k is equal from 1 to infinity of 1 over k minus 1 over n plus k. Now this is a popular formula for a generalization of the harmonic numbers, but you can reduce it to the finite form. And here it is going to be the same thing since we're looking integer order, nth integral. So this is just going to be x to the n times ln of x minus the nth harmonic number all over n factorial. So you see with these things, we need some usage from some special functions, special identities. So it's not as elementary compared to single order derivatives and integrals. Let's look at a simpler example, testing the Riemann-Liouville fractional derivative. Let's check if our result for the half derivative of x is the same as we saw before. When we plug this into the formula, we're going to get 1 over gamma of a half, that's root pi, times the integer order derivative. Again, we're going to choose base point 0 since that is where polynomials or power functions vanish, specifically monomials here. But so all the way to x of t over root x minus t dt. Now we're going to make another substitution. U is equal to x minus t to simplify things. We're going to get 1 over root pi times d over dx of the integral from 0 to x of x minus u over root u du. Now this is just a simple antiderivative. We're going to get 2x times root u minus 2u to the 3 over 2 over 3. This goes from 0 to x. And now you can simplify this easily. It's just 4 over 3 times root pi. We're going to have this outer derivative remaining of x to the 3 over 2. And then once you do this, you end up again with 2 over 2 of root x over pi. So this matches up with our definition from before. Now we're going to look at an alternative definition. An alternative definition using limits, a little bit similar to the limit definition of a derivative, kind of going from there. So this is going to be what's called the Grunwald-Letnikov fractional derivative. And we're going to start from finding the nth derivative as a limit and then generalizing again like before with using gamma function, or we'll see things with generalized binomial coefficients here. But we're going to start from the standard limit definition. Lim h approaching 0 of f of x plus h minus f of x all over h. Alright, so this is standard. Now we're going to use the second derivative here. If we plug this in, of f prime of x plus h minus f prime of x divided by h. And now we're going to substitute in the difference quotient here. Note that this can be made justified by the mean value theorem to use the same h over here, and we're going to do this further as we keep iterating this idea. But we're going to simplify. So now you see here we have f of x plus 2h minus 2f of x plus h plus f of x over h squared. And doing it one more time, so here, now we have f of x plus 3h minus 3f of x plus 2h plus 3f of x plus h minus f of x all over h cubed. Now you can see here the patterns: h, then h squared, then h cubed, 1, 1. You have 1, 2, 1. Then here you have 1, 3, 3, 1. And the signs are alternating. You can see these are clearly Pascal's triangle binomial coefficients here. And so, in general, we have the following nth derivative formula as a limit. This resembles a lot from the binomial theorem. So we have the binomial coefficient here, the alternating sign, and then f of x plus n minus m times h. Okay, and then the simple way to generalize for the fractional derivative. One thing to notice, here's a way to help out the generalization, is that if we let n here go to infinity, this doesn't change the sum at all, because n choose n plus 1, n choose n plus any positive integer all goes out to 0. So all the remaining terms go out to 0. So we can just keep this here as the infinite sum in the generalization. And this is similar to how you arrive to the generalized binomial theorem. So that is going to be the Grunwald-Letnikov fractional derivative. Now let's take a look at one example here. So we're going to take a look at the Grunwald-Letnikov derivative of cosine, fractional derivative, alphath order, and we're going to see if it matches up with our previous derivation just from looking at patterns at the beginning. So this is what we have over here. Now we're going to exploit the fact that cosine is the real part of the complex exponential and simplify some things over here. Alright, so over here you can see that we have the structure of the binomial theorem. Specifically, we have e to the I times h, e to the I h minus 1, and it's to the power of alpha. So we're going to get here the real part of e to the ix, pull out the alpha. We're going to have limit as h approaches 0 of e to the ih minus 1 over h. This is all to the alpha over here. And this is a well-known limit. It's actually going to be the natural log of our base over here. We have natural log of e to the I, which is just equal to I. And so, obviously, we're going to get the real part of I to the alpha e to the ix. And you know that this is just going to be equal to cosine of x plus alpha pi over 2. So this matches up with our previous results. Another thing to look at, which maybe some people, if they already did complex analysis, would jump to, would be Cauchy's differentiation formula. So there is an expression to get the nth derivative as a contour integral. For those that aren't familiar, I'm going to start with Cauchy's integral formula and then differentiate it n times, and we'll see how we arrive there. This is a loose proof, it's not fully rigorous, but basically we have 1 over 2 pi I times the contour integral over c of f of w over w minus a dw. Now c is a closed contour that for any path, any contour that closes in on the point A. It has a inside it, and now we can, it all just depends on where you are with the singularity, so we can just consider a simpler contour, which will just be, we'll take a circle with an infinitesimally small radius. We'll take the limit of a radius epsilon approaches 0 of the contour integral for this circle here of f of w over w minus a dw. And now again, since epsilon is approaching 0, the radius is approaching 0, f of w is pretty close to f of a in the limit. So we have 1 over 2 pi I times the limit as epsilon approaches 0, radius epsilon here, of f of a times w minus a dw, and this 1 over w minus a can just be done using a common result. With direct parametrization, we're going to have w is equal to a plus epsilon e to the it. This is just the parametrization of the circle in the complex plane. So we have 1 over 2 pi I times the limit, epsilon approaching 0, so the derivative of this w over here, we get I epsilon e to the it, so we can pull out an I epsilon. We can also pull out f of a over here, and so we just have the integral full circle, so 0 to 2 pi, of, we have another e to the it over here, then the w minus a just becomes epsilon e to the it dt. And so here we have a lot of cancellations. So this epsilon cancels with this epsilon, and the e to the it cancel out here. And so in the end, we're just going to get 1 over 2 pi I times 2 pi I times f of a And obviously these guys are going to cancel, and we're just going to get f of a. And so then using differentiation under the integral sign n times, again we know it's simple here for power functions, we're just going to get that the nth derivative at a is going to be equal to, we have an n factorial prefactor now, n factorial over 2 pi I times the contour integral over c of f of w over w minus a to the n plus 1 dw. So this is Cauchy's differentiation formula. And indeed, as far as I know, you can also use this for fractional derivatives. Again, using the gamma function over here. And one thing to note though for contour integrals is that with fractional powers here, or real number or complex powers, you have to be careful of the branch cuts for fractional order. We can actually show, showing here on screen, that the Grunwald-Letnikov derivative is actually equivalent to Cauchy's differentiation formula here. Obviously it's less slow to get from there than just differentiating Cauchy's integral formula n times, since I literally used that in the proof, but it shows that this is actually an equivalence definition here, so you could use either or. Another brief way, if you know about integral transforms, to define a fractional derivative is to use formulas for things like Laplace or Fourier transforms of nth derivatives, and then just taking the inverse transform on the outside. So if we're looking at the Laplace transform, you can basically define the fractional order derivative to be equal to the inverse Laplace transform of, so we get an s to the alpha prefactor of the Laplace transform of f of x over here. Though usually more useful, since this converges for more of them, you would have the Fourier transform. We can use the fact that we have the fractional derivative is going to be the inverse Fourier transform of, we have an I omega prefactor here raised to the alpha, of the Fourier transform of f of x. So this is another way to get to it. It's a little bit shorter, more compact. But again, these could also be quite restrictive depending on the existence or convergence of the transform. Now we're going to look at, well, specifically one type of formula for fractional derivatives, since not everything generalizes other than linearity to an understandable degree. So we can have a nice formula specifically for a product rule of fractional derivatives. And again, we're going to start from the integer order rule, what's called Leibniz's rule. I'm just going to do a quick derivation here. So, given power series, where we have f of x to be the sum n, m is equal from 0 to infinity of f of m at a over m factorial times x minus a to the m, and g of x is equal to sum k from 0 to infinity of the kth derivative of g at a over k factorial times x minus a to the k. We can consider the product of these power series. So the product of these, we're going to multiply in the sums, it becomes a double sum. M is equal from 0 to infinity of sum k is equal from 0 to infinity of f, mth derivative at a, g, the kth derivative of g at a, divided by m factorial times k factorial times x minus a to the m plus k. Okay, now we're going to do change of variables here. We're going to let n be equal to m plus k, and we're going to have the new bounds here, outer bounds here, of n bounded from 0 to infinity, and we're going to let k, which is equal to n minus m, be indexed by m And now m over here, we can rewrite the bounds from 0 all the way up to n. Okay? So now we can rewrite this double sum as the sum from n is equal from 0 to infinity of the sum m is equal from 0 to n of mth derivative of f at a times g to the n minus mth derivative at a over m factorial times n minus m factorial times x minus a to the n. And now we're going to multiply and divide by n factorial, so we get a binomial coefficient here, and we get the form of the power series of the coefficient. And just extract from there, we're going to get 1 over n factorial, the inner sum here. M is equal from 0 to n of, so again, you add the n factorial on top here, so you're going to get n choose m times f of m at the mth derivative of f at a, and then g n minus mth derivative at a times x minus a to the n. And so clearly, by coefficient extraction here, and Taylor's formula, that this is just going to be the nth derivative of f times g at a. And so that then means that we can define the fractional order derivative. Again, similar to the Grunwald-Letnikov thing, the upper bound of the sum can go to infinity. Okay, so we have this formula, and this is actually somewhat decently usable compared to some of the other ones, though, for example, for something like chain rule, it's way more complicated and definitely way less practical to use, and not a lot of closed forms you can find, just showing here on screen. It comes from generalizing the nth derivative chain rule formula. Fadi-Bruno's formula is already complicated, and this just makes things more complicated. But yeah, basically, the main things you really have that are usable are this, and obviously linearity, which comes as given. So this was a general introduction, though there's definitely way more to expand on here. Like, there are many more definitions of fractional derivatives with different pros and cons. Some applications, while there are a few, such as to the tautochrome problem, basically where you have a curve with different equally spaced balls that makes them all approach the endpoint at the same time. You can actually solve that more simply using fractional calculus. And then there's things like fractional differential equations, which can be used to model systems with non-locality. In fact, I found a paper from my own university, York University, that features a basic introduction to modeling with fractional differential equations, which you can see in my sources in the description, and a bunch of other further reading. So I hope you enjoyed this video. It's been a long time coming. I actually learned this as early as 2022, but I kind of pushed it back too far. But I'm glad to finally have this video out, and I hope you found it interesting, all these generalizations, and I hope to see you in the next video. Goodbye.